So in this video, we're going to have a bunch of definitions to start off with. We're going to define our empirical formula, our molecular formula, and then our empirical and molecular masses. And then we want to be able to go back and forth from if we're given empirical formula, finding our molecular formula, or empirical mass and finding our molecular mass, and interconverting between all of those. So first off, let's talk about the definitions. We're going to start with our molecular formula and our molecular mass. So this is the formula that actually describes what an individual molecule is. So take something like this. The molecular formula for this, if you count up all of your carbons or all of your black atoms, and you count up all of your oxygens or all of your red atoms, and you count up all of your hydrogens or all of your white atoms, you get C6H12O6. Our molecular mass describes the mass of this. So you go to the periodic table, and we talked about this in sort of some of the intro videos and things of that sort. So we have a basic idea of how to go about calculating the molecular mass from the periodic table. But we add all of our molecular masses up. So 6 carbons, 12 hydrogens, and 16 oxygens to get, in this case, 180.16. We can talk about this in terms of grams per mole or AMU. Again, all of that was kind of discussed in some of those really early on introduction videos. Where I want to kind of compare this is comparing this to the empirical formula. An empirical formula is a little bit different than a molecular formula in that it's the lowest ratio. So C6H12O6, we can reduce that if we're thinking about fractions and turn that into CH2O. This does not do a very good job of describing the molecule, of course, because, well, CH2O is not the same thing as C6H12O6. But there's many, many times where on our way to getting the molecular formula, we're going to have to go through empirical formula. And from an experimental standpoint, it's very common to be able to easily figure out the empirical formula while having to do some extra work to get the molecular formula. Empirical formulas, we call their masses a formula mass. It's the same idea as a molecular mass where you're going to take all of your masses off the periodic table, so 12 for carbon, 1 for hydrogen, 16 for oxygen, and add it up. Now, we want to be able to go in between these. So very commonly, you'll have an empirical formula, or you'll be able to solve for it. And you'll be given a molecular mass. That's usually the most common way of doing this, but as with all problems, you want to be able to do it in all directions. So let's look at how these are related. They're always going to be related by a whole number ratio. So if we take our example from the previous few slides, and we have CH2O and we have C6H12O6, they're related by a factor of 6. Our masses are related by the same factor. So our 30 AMUs for our empirical formula translates into our 180 AMU for our molecular formula. Now, why is this useful? Well, this lets us go back and forth between everything using ratios. All right, so let's take something where we have an empirical formula and we have a molecular mass, and we're going to use that to find the molecular formula. This is a very common piece of a problem where you've done a bunch of work to get to this point, and now you have this little section you have to add in. So it's worth just talking about on its own, but recognize that this is like a baby step in a much bigger problem for the most part. So if we have our empirical mass, we know that if we times that by some number, we're going to get our molecular mass. Now, I didn't give you an empirical mass exactly, but I gave you the empirical formula. And if I give you the empirical formula, you can go to the periodic table and you can solve for the empirical mass, or the formula mass, if you want to think about it that way. So let's take the molecular mass that the problem gives you, the 109.22, and if we divide that by our empirical mass, we're going to get this ratio that we need to multiply everything by. So we take our 194.22, we divide it by our 97.11. If you're saying, wait, where did you get the 97.11 from? Well, you add everything up. You add up the carbons and the hydrogens and the nitrogens and the oxygens, and you get our 97. That gives us a ratio of 2. Depending on when you go ahead and add this, and depending on the sig figs and the rounding errors and all of these, maybe you get something like 2.001 or maybe you get something like 1.998. Just round it to the whole number. If you get like 1.5 or something of that sort, you probably have done something wrong and you need to look things over. But slight rounding errors happen. Now, this 2 tells us what we have to multiply our empirical formula by to get our molecular formula. So we take our empirical formula that I gave you in the problem, we multiply every single element by 2, and we get our molecular formula. Now, again, this is a very, very common piece of a problem. So I wanted to give you a little bit of sort of homework problem-solving help tip, which is you're going to be a lot of times told, hey, find the molecular formula using, and then they're going to just throw a bunch of data at you. Pretty much for all of these, the general rule is get to moles. So don't think of you have a whole lot of these, don't think of all of them as different problems. Just think of, okay, how can I take this data they gave me, and how can I get to moles of an individual element? Sometimes it'll be the same element that they give you, sometimes it'll be different. But this way you have a sort of overarching theme to all of those problems, get to moles. And you really know how to do most of that already. Your high school classes tended to do a very good job of helping you get there. So that will help you solve all of those problems. Another tip, and we're going to have an example of this in a later video, a lot of times you'll also be given a bunch of data about a sample or a type of situation, and you won't actually be given the amount of the sample. So this will come up in a lot of molecular composition questions, which we'll talk about in specific in the next video. But this will usually require just assuming a sample size. Assume whatever you want. You can assume a 1.5 gram sample if you want, but that's going to make your math difficult. So the simplest thing to do whenever you're not given a sample size is assume a 100 gram sample. And we'll do some specific examples of these in individual videos, but I can't do them all because there's just a million different types of questions. So this kind of gets you started on them and gives you a starting point for all of the problems. So in summary, we have our molecular formula, which is the formula that actually describes an individual molecule. We have our molecular mass, which is the mass in either grams per mole or AMU of that molecular formula. And then we have the empirical formula and the empirical mass, and that's based on the lowest whole number ratio. So our lowest whole number ratio is described by our empirical formula, and the mass that comes out from calculating that is our empirical mass, or our formula mass. You'll hear it called both. Your molecular mass is always going to be a whole number ratio of your empirical mass, and it's going to be the same whole number ratio as your molecular formula is to your empirical formula.